Hey, welcome to Git Behind the Scenes. Today we're going to be talking about Git internals. Let's start by introducing myself. My name is Corbin Crutchley. I'm the CTO of OceanBit, and we make GitShark, which is an open source mobile Git GUI. You can clone your repositories, modify files, push them back, anything that a desktop Git GUI would do, but from your phone or tablet. So today in our talk, we're going to be talking about what the Git folder is and how it's utilized internally in Git, what data structures are used, what really happens in Git during common operations, and how to recover from specific data loss that may occur within your repositories. Let's go ahead and start by trying to understand the Git folder a little bit. So the Git folder is a folder that lives inside of every single repository that you have locally on your machine. It is stored under .git, and it contains multiple files that are utilized to track your code base. So for example, here we can see that there is a file tree that contains multiple different files. This is filtered just for focus, but these are going to be the main files that we're going to talk about that Git uses internally. Let's start by taking a look at the hooks folder. So Git hooks are a way of injecting user functionality into common Git operations. So for example, when we initialize a new repository, we can see in the hooks directory that we have multiple different files that are generated with the .sample extension. Now, if we remove the .sample extension, these executables or scripts might run during operations. So for example, if we rename commit message.sample to just commit message, that script will then run after we make a commit message, but before the commit is actually made. This will allow us to do some things such as formatting commit messages to match a standard pattern that we're looking for. There are 17 different types of hooks. All of them hook into different methods of doing things. So for example, here, if we cat our commit message script that we've built, we can see that we're running a program called commitlint. Commitlint checks to make sure that we're following a standard practice for all of our commit messages. And here we can see that when we commit with a message that doesn't follow that practice, it gives us a warning that type and subject may not match what we're looking for. So the easiest way to get around that would be to simply fix our commit message so that it adds fix to the list of things that we're doing in this commit. But we can also run the no verify command in the git command, which will allow us to bypass those hooks. So some other operations that can be handled using git hooks might be running linting before making a commit, which would then make the changes to the file, stage those files, and include those changes into your commit. You could also run unit tests before making a git push. There's all sorts of things that might help prevent you from making mistakes when you're pushing to branches that have vital resources in them. So now that we've understood the hooks folder within the main Git folder, let's explore something else within the Git folder itself, the index file. Here, this defines the staging area. We can see that whenever we run a git add, git remove, anything like that. And if we try to cat the file using either cat or head or one of those commands, we'll see that a lot of the output is a little garbled, right? So we can see here that it says dirc, something along those lines, right? That's because it's stored in a binary file, which makes it easier for Git and computer programs to read, but a little harder for us to read. Let's go ahead and run the ls files command, where we can see here that there are 3 files that are tracked for this index file. There's the buck config, the ESLint, and the git attributes. Now, Git contains metadata on each of these files in the index, which type of file it is, and others associated information, but it does not store information about folders. This is why if you've ever tried to track a folder, you'll know that you have to have a file usually called git keep. That's because Git's index doesn't know how to really handle empty folders on its own. You have to have a file, and that path should represent it. So an addendum to the index file, there's also the head file, right, which is another file in the Git folder. This tracks what is currently checked out. So if you were to run a checkout command, it would update this. And we can see that if we cat the head file, it shows us a ref, right? So ref's head's main. But like, what's a ref, right? A ref can be one of 3 different things. It can be a head, which is branches. It can be a remote, or it can be a tag. Now, remotes are also very similarly branches, but they're stored in whatever cloud Git provider you have, GitLab, hub, anything of that kind. And if we go ahead and cat one of the files, here we can see our refs head main. And if we read that file out, it shows an ID for an object. So let's go find that object. If we go ask Git what that object is, we look up the ID using the cat file command, we can see that it is a commit object. So a commit object is created during a git commit, which makes sense. But if we run the git-p, cat file-p command, we can see that it contains information about the file tree that's associated with the commit, what files were present, which parent commit does it track so that we can run commands later, such as git log. We see information about the author, committer, and the commit message, right? So this is a commit object, but there are other types of objects as well. There's tree, which stores information about a directory tree. There's commits, which is the snapshot of your changes. There's blob, which is a file's contents. And there's a tag, which is kind of like a named ref. All objects share some common properties. For example, all of them live within an objects folder that is stored within the .git folder. All of their paths are a SHA-1 of their contents. So for example, here we can see 18FAE. That is the start of a SHA-sum that matches the contents. And all objects are compressed with zlib. So we can see that by trying to cat the previous file. And we'll see that there's a lot of symbols here that we're probably not familiar with. And that's because it is compressed. So if we run that file's contents through the inflate command to decompress the zlib information, we can see that we have the commit object and we're reading the file contents as expected. As mentioned before, the file path is a SHA-1. So if, for example, we cat the file, inflate it, and run it through SHA-sum, we can then see that it has the same exact ID that it utilizes for the path. Pretty neat. So now that we've understood objects a little bit better, what are different types of objects outside of commit, right? We've talked about them before. There's the tree object, right? This is also created during a git commit to track what files are tracked with that commit. It contains a list of files and other trees. So for example, here we can see that buckconfig and eslint are both blobs, but the source object here is another tree, which would be another list of files. So that's how it handles subdomains. And each of these entries has metadata, right? So it has the name of the path or file. It has the type of file that's being stored or type of information, and it has the ID. However, something worth mentioning is that it doesn't contain the file's contents. So if we try to find that blob information, we have to go track down that ID. So speaking of, that's where blob objects come into play. Blob objects are created actually during the git add command, which is when you're staging the files. It goes ahead and creates the blob object. And while it contains the binary data, for example, this file used to be a git ignore file, it does not contain any metadata about the file. This includes otherwise commonplace metadata such as the blob's original file name. So in order to get a blob's name, we would need to go reference the tree where the blob is referenced, and that tree is then, of course, is contained within a commit object. So there's a hierarchical relationship between these different objects. So let's do a quick recap of what we just talked about with objects and refs. Let's go ahead and start by creating an empty directory. We'll verify that it's empty, nothing in there. We'll then git initialize that directory so that we can see that the default files in .git folder are created. Notice that there's nothing in objects currently. We'll go ahead and fix that by creating a new file, right, called hello.txt. We'll verify that the file's contents have been written using a cat. Then we can add the objects using a git add and a git commit, right? The git add will create the blob objects and the git commit will create a tree and commit object. We'll go ahead and create a second set of objects using a new file or an update to the existing file. Now we'll git add that and git commit that. Now we can see that the file has been created. And if we look into the objects folder within Git, we can see that there's a few new folders here. Let's go ahead and check out what all of the new objects are. Here we can see that there are 2 sets of 3 of blob, commits, and trees. We can verify that these were created when we would have expected them by git cat filing the first commit ID. This contains our initial commit, which references the tree, and that tree would then reference the blob. Now we can run git cat file on the second commit. Here we see that this is our most recent commit, so it includes a parent reference to the first commit, and that ID should be referenced within our newest ref. Let's verify that. Here we can see that there's a new ref created for master, and if we read the contents of that ref, we should expect to see the ID of the most recent commit, since our branch is pointed to it. We see that they match, and that's as we would expect it to be. Something worth mentioning that had come up during that video is that we were updating an existing file. By default, Git will track multiple versions of the files as full blob objects. What this means is that if we had a 1 megabyte myfile blob object, even if we made a tiny update to that file and added that in a future commit, it would store both full versions of the file. So here we can see that the size of my file is 1.1 megabytes. When we git add and git commit, our git objects folder is now 1.1 megabytes. Then later, with updating just a single line of code within my file, we can see that the file contents of objects remains the same. But once we git add and git commit that update, we can see that git objects is now 2 megabytes. This is important to keep in mind because it means that big repositories with multiple years of history, for example, would bloat in size unimaginable, right? So how does Git solve this? Git solves this by using a command called gitgc, which stands for Git Garbage Collection. What this command does is it compresses multiple objects into a single file. So here, within our Git objects folder, we can see that there is 6 entries, which are all objects. We'll check the size of this object folder, which is 60 kilobytes right now. And because there are some files that are duplicated, when we run gitgc, if we go tree this directory again, we'll see that everything has been compressed down to 1 or 2 files. And now the size has gone from 60 kilobytes down to 24 kilobytes. This command is ran automatically when needed, usually during occasional operations. So say you run a git checkout or a git fetch, it may automatically run gitgc for you. And this single file is called a Pac file. So let's talk a little bit more about Pac files. What really are they? A Pac file contains many objects within one file. While the Pac file itself is not compressed with zlib, remember that the objects stored inside are still compressed with zlib. While the Pac file has a .pac extension, there's also a complementary index file which has the .idx extension, and this index file simply makes unpacking individual objects much faster from the Pac file. So when you need to pull out blobs using git checkout, it's a lot faster. Now Pac files are able to reduce the file size using a concept of deltas. Deltas are a way to save space when you have multiple versions of the same file. The way that this works is that it stores the differences between the different variations that have come across over time. We only store the latest blob, and when we need an older version, we can reconstruct it using those differences. So, for example, if we've had 3 versions of a file, we'll keep only the latest version of the file, and when we need to get the older versions, we simply apply the differences between those files that were changed each time. We can see an example of this using a command like gitdiff, but it's important to remember that the way that gitdiff and the way that deltas store those changes between versions are significantly different under the hood. This is simply an example of how diffs might look in a more human approachable environment. So Pac files can also live alongside objects. So if we were to run gitgc and only have our Pac and index files, and then later add a new file, git add, git commit them to create new objects. If we ls the git objects directory, we would see our Pac files, yes, but we'd also see 3 new objects that are not part of that Pac file. These objects that are not packed are called loose objects. These loose objects can then later be included in their own Pac files when gitgc may run automatically. It's important to remember that gitgc will only really be doing this after a substantial size of the repo has been noticed. Pac files are also noticeable whenever we're utilizing network operations. So, for example, if we're running git push or git pull, all of the files will be compressed into a Pac file in order to be shipped down the pipeline. This is true for fetch, and because it is true for fetch, it is also true for git cloning as well, because under the hood, git cloning utilizes fetching. We can see this in our video example. Here, we'll run a git clone. Once that git clone is completed, we will see that the objects are as we would expect to see, and all the files have been created. We'll tree the Git folder to see that we have our objects in Pac files and we have our refs that have been created. But let's go ahead and clone this repository manually. Here, we'll create a new directory called gitshark. We'll then cd into this directory and run git init. We'll verify that the Git directory is empty currently, except for the default files. We can run git remote add origin to add the remote URL to fetch from later. But we'll notice that if we look in our Git folder, that the contents haven't really shifted that much. This is because the only thing git remote add does is update the config file. If we cat the git config file, we can see a new entry for a remote origin, which contains our URL to fetch from. Let's go ahead and run that fetch. Now, if we take a look inside of our Git folder, we can see that while our objects have been created through Pac files, we don't have any files that are part of our working tree yet. So let's go ahead and do that by running a git checkout, which will create the files locally and create a ref branch for our main head. Speaking of the config file, let's take a look at it. Config files, unlike objects, are not zlib compressed, meaning that we can take a look at them as plain text files. The config file contains repository settings, informations about remotes, which we saw earlier when we were trying to fetch files, and it also contains information about tracked branches, meaning that if we tell Git to track a branch, when it goes to grab the information from the remote, it will look in the config file first to know where to look. Now that we understand the Git folder a little bit better, let's take a look at some methods of recovery that we can do utilizing some of Git's internals. Now, we've all been there. We've made commits that we haven't wanted to make. For example, here I created a file called accident.ono and made a commit of it, right? But let's say that I wanted to get rid of that commit later on. I ran a git log, realized I didn't quite want it there, so I ran a git reset hard to remove that commit. But oh no, in that commit, I had also included an important file I still needed. Is that content lost? Luckily for us, it's not. This is where our log folder comes into play. Our log folder is updated every time that a ref is updated, meaning that we have made a commit or changed the reference in some way. In this example, if we were to look in our log folder, we can see that under logs refs head main, that we've made a clone. We were able to make a commit, and later we were able to reset from that commit. Because of this log file, we're able to still see the object ID of that commit. While the reset has updated the head, it has not removed the local objects. This means that we can go check out that commit and still grab the files that we need, which are important. This log functionality can be accessed using Git's reflog command. By default, it will show the head log of what you have checked out yourself, but you can select other refs using this command simply by providing the name of that ref. So if you want to see which commits have been changed for a ref of another branch, you can simply run git reflog and point to that reference. While git reset can be a beneficial tool for updating a ref, it is important to note that local objects are not modified. This means that even if you're doing a rebase or first push, you are still able to track your objects in the object folder. They haven't been removed. However, because they're not referenced by a ref anymore, for example, they're not part of a branch's log, they're called unreachable objects. Now, gitgc by default removes these objects after 2 weeks or more, assuming that gitgc has ran during a different operation, but otherwise this data may be able to be recoverable. First, let's understand how we can create unreachable objects, whether intentional or otherwise. Common methods of creating unreachable objects include rebasing, maybe rebasing interactively and dropping commits that way. Squash merging is another way that unreachable commit objects and those trees can be created. Or even something as simple as running git add and then changing your mind a little bit later and running git add before you made another commit. For example, if we take this fresh directory that we've created with git init, add a hello.txt file, and git add it, we can see that one git blob object has been created that starts with the SHA-SUM of 2.1. Later, if we were to change the file's contents and rerun git add, we'll see that there are now 2 git blob objects, 2.1 and 5b. This is important to note because if you make a commit after this point, only object 5b will be tracked. 2.1 will be known as an unreachable object, in this case a blob object. We can find these unreachable objects with git fsck, which stands for Git File System Check. Let's go ahead and run it. Given the example from before, where we've reset hard on the main branch, we'll see that git fsck doesn't actually give us any information, but we know there's an unreachable commit because we've reset it. It's important to note that git fsck does not show unreachable commit objects that are tracked within the logs folder. So temporarily, let's go ahead and get rid of that folder. Now, if we rerun git fsck, we can see that there is a commit with a commit ID, but it tells us it's dangling. What's that? And why does git fsck select it by default? Well, there are 2 different types of unreachable objects. There are dangling objects and traditional unreachable objects. Unreachable objects are objects that are not reachable by any ref. So this means that the tree, blob, and commit objects that are shown in the side are not part of any ref, not part of a branch or tag or anything like that. Dangling objects are a subset of unreachable objects with one additional stipulation. They may not be referenced by other unreachable objects. So, for example, in the unreachable example, we have a commit, blob, and tree. However, the tree references the blob and the commit references the tree. Because of this, when we don't use the unreachable flag with git fsck, it only shows us the commit is dangling, as that is the only dangling object. Let's do a quick review of what we've learned in the last few slides. Let's start in my terminal where I have a folder open. This is my real Git folder for GitShark's development. I'll prove this to you by running git reflog and showing just how many changes I've made within head on my local machine. As we've seen before, if this repo were freshly cloned, this reflog would only have one entry in it. Because I often utilize interactive rebases during experimental development that I later then clean up in preparation for merging into my deployment branch, there's bound to be many unreachable objects here. Let's go ahead and run git fsck. That's a lot of dangling objects. For each of the dangling commits that we see, we know that there's even more unreachable trees and blobs that we aren't seeing currently. While we could run gitgc to clean these items up, that would also place the rest of the objects inside of a Pac file. Instead, let's go ahead and run git prune to only remove unreachable objects. We can verify these objects were removed by running git fsck again. Now that we've pruned unreachable objects, let's go ahead and pack them up to save some storage space. We'll start by listing the folders in the objects folder to verify that we do have loose objects. Then, we'll pack the files using gitgc. Once this is done, we can see that there are no longer any loose objects. That's all we're going to talk about today, but I'd like to provide a special thank you to William Hilton, who's been absolutely instrumental in our understanding of Git here at OceanBit, and of James Coughlin, whose book, Building Git, has been fantastic in helping us get up and running. You can find us at OceanBit on Twitter, OceanBit at GitHub, or even my own Twitch, which is Crutchcorn, where we've built a significant portion of GitShark live on stream. Thanks, and take care.